I'm David Bombal, and I want to welcome you to this Piketty.com presentation. In this video, we are continuing the discussion about OpenFlow and software-defined networking, or SDN. In this video, I'm going to explain and demonstrate OpenFlow pipelines on physical switches. I want to give you an overview of what the pipeline looks like in OpenFlow 1.0 versus 1.1, 1.2, 1.3, and 1.4. In brief, the big difference is in OpenFlow 1.0, only a single table was supported, whereas from OpenFlow 1.1, a multi-table pipeline was supported. As always, I want to keep these videos practical, so I'm going to start off showing you the pipeline on a 3500 YL switch. This is an HP switch configured with OpenFlow 1.0. Then we'll look at another switch configured with OpenFlow 1.3, and we'll move on to looking at a 3800 HP ProVision switch running OpenFlow 1.3, as well as a 5900 Comware switch running OpenFlow 1.3. We'll view the results on both an HP VAN SDN Controller so that you can see the differences between OpenFlow 1.0 and 1.3, as well as on the HP switches themselves. So I'll show you the output of the OpenFlow table on the 3500 YL running OpenFlow 1.0, and then I'll show you various switches, 3500 YL, 3800, and 5900 running OpenFlow 1.3. Hopefully this video will not only explain the theory of an OpenFlow pipeline, but also allow you to see it in practice, with traffic being transmitted through a switch running OpenFlow 1.0, as well as switches running OpenFlow 1.3. The reason why I'm going to demonstrate on OpenFlow 1.3 is that at the time of this recording, HP switches do not support OpenFlow 1.4. The highest release of OpenFlow that they support is 1.3. But a multiple table pipeline was introduced in OpenFlow 1.1. So that won't affect this demonstration. Now, before I get into the details, in this video, I'm going to show you and explain why on the HP VAN SDN Controller, a version 1.0 switch shows NA in the table ID. Why does this switch show table 100 and 200? Why are flow entries put into table 200 rather than in table 100? Whereas on this switch, entries have been put into table 100. Is this a hardware-based table or a software-based table? On a Comware-based switch, why do we only have table 0? So I'm going to spend quite a bit of time showing you and explaining tables and pipelines, but there won't be enough time to explain everything. So I will create subsequent videos with even more detail explaining what can be matched in hardware on a Comware-based switch versus what can be matched in hardware or software on a ProVision switch. Does it matter, as an example, whether we're using a 3500 YL, which is what we've got in this example with the NA and this example? Does it matter if you put version 1 ASICs and version 2 ASICs into a switch? So we'll defer that to another video. In this video, I want to show you the difference between an OpenFlow 1.0 switch versus an OpenFlow 1.3 switch, and explain a bit about the pipelines. Now, there's no better place to get OpenFlow information than the Open Networking Foundation's website. So here on the Open Networking Foundation's website, under SDN Resources, you can get details of the ONF specifications including OpenFlow, OpenFlow Config, OpenFlow Test, OpenFlow Conformance, and other information. So let's look at the OpenFlow specifications. The various OpenFlow specifications are listed here. In the lab, on the HP switches, the OpenFlow in use is OpenFlow 1.3.1. However, let's look at the OpenFlow switch specification 1.4.0 and look at multiple table support. So OpenFlow 1.4.0 was released on the 14th of October 2013. Scrolling down, and there's a lot of information here, and I won't bother trying to explain all of it now. I will take pieces of the specification and explain it in other videos. So firstly, we have an introduction. This document describes the requirements of an OpenFlow switch. As you can see here, an OpenFlow switch has an OpenFlow table pipeline. OpenFlow 1.0 only supported a single table, but from OpenFlow 1.1 as mentioned, multiple tables are supported in the pipeline. An OpenFlow switch runs an OpenFlow agent that communicates to an OpenFlow controller using the OpenFlow protocol. Now, in the version we're using in the lab, the port number used is TCP port 6633. That has changed with the IANA, or Internet Assigned Numbers Authority, allocating 6653 to the Open Networking Foundation. But for this video, that won't affect things because we're going to concentrate on the OpenFlow pipeline. Now, Section 2 discusses switch components. And as you can see here, an OpenFlow switch consists of either one or more flow tables and a group table which perform packet lookups and forwarding, and an OpenFlow channel to an external controller, which I've shown you here. The switch communicates with the controller, and the controller manages the switch via the OpenFlow protocol. Now, using the OpenFlow protocol, the controller can add, update, and delete flow entries in flow tables either reactively, in response to packets, and proactively. I'll discuss more details about matching the priority of flow entries in the tables, what flow misses are, and so forth in other videos. What I want to point out here is some of the information in the OpenFlow tables section. I'd strongly recommend that you read the OpenFlow specification to get details of how this functions. I want to explain it in brief terms and then show you a practical example. Essentially what happens, however, is when a packet arrives, it will hit the first table in the OpenFlow pipeline and then could be forwarded out of a port or by using a goto statement be sent to another table. Now, before going any further, I want to point this out. The OpenFlow pipeline of every OpenFlow switch contains multiple flow tables, each flow table containing multiple flow entries. The OpenFlow pipeline processing defines how packets interact with those flow tables. And this is the important piece. An OpenFlow switch is required to have at least one flow table and can optionally have more flow tables. An OpenFlow switch with only a single table is valid, and in this case, pipeline processing is greatly simplified. So to be compliant with the OpenFlow standard, an OpenFlow vendor switch needs to have at least one table. So practically, when I demonstrate this, you'll notice that a Comware-based HP switch has only one hardware table. The switch runs OpenFlow 1.3 and is compliant with the standard because only a single table is required to be compliant. HP ProVision switches, on the other hand, support multiple OpenFlow tables, and that's also dependent on the mode used on the switch. On ProVision switches, you have this option to use IP control table mode, which increases the number of tables in the pipeline. Now, scrolling down a bit further, the flow tables of an OpenFlow switch are sequentially numbered starting at 0. Pipeline processing always starts at the first flow table. The packet is first matched against flow entries of flow table 0. Other flow tables may be used depending on the outcome of the match in the first table. So as an example, on an HP ProVision switch, we could have 3 tables. Table 0, Table 100, and Table 200. When traffic arrives, it starts at Table 0. Traffic could then be forwarded to Table 100 and then onto Table 200. Now, as per the OpenFlow standard, you cannot go back In other words, you're always going to an increasing table number or ascending table number. So traffic can be sent from table 0 to table 100 and to 200, but couldn't be sent from table 200 to table 100 or to table 0. Now on an HP ProVision switch, these tables are hardware-based tables. In other words, tables 0 and 100 are stored in ASICs or in hardware. Table 200 is a software-based table. The advantage of sending traffic using an ASIC is speed and scalability. Software tables generally provide more features, but are a lot slower. A Comware-based switch by default only has one table, which is a hardware-based table, table 0. So when traffic arrives, traffic is processed using that hardware table. But on a ProVision switch, as an example, traffic could be matched in table 100 and then forwarded out of a port. So the action could be send the traffic out of port 2. But there could also be a go-to statement stating that some traffic needs to go to table 200 for further processing. A big difference between OpenFlow 1.0 and OpenFlow 1.3 is that an OpenFlow 1.0 switch is viewed as a single table. The controller has no visibility of the hardware tables or software tables available on that switch. On an HP VAN SDN Controller, as an example, the table ID is set to NA. In other words, non-applicable. The controller has no visibility of the hardware or software tables on the switch. As I'm going to show you in a moment, on an HP ProVision switch, the controller will be able to see the hardware tables and software tables available on that switch. Now, by default, on HP ProVision switches, when they negotiate to use OpenFlow 1.3 with a controller, they will use these three tables. Now, you can add additional software tables. By using the command IP control table mode, you can increase the number of hardware tables available on the HP ProVision switches. This is hardware dependent, and at the moment it's not recommended that you use IP control table mode with a controller. It's recommended that you stick with the defaults. So you can't increase the number of hardware tables or software tables on the switches apart from what the vendor has determined. As an example, on ProVision switches, you can increase the number of software tables used from 1 to 4, using tables 200 to 203. Those kind of restrictions are set by the manufacturer. As an example, once again, on Comware-based switches, you only have one hardware-based table. You cannot add 10 software-based tables, as an example. A Comware switch does allow you to have an additional hardware-based table, so you could have table 0 and table 1. And we won't get into the discussion of those in this video. I want to practically show you the differences between OpenFlow 1.0 and 1.3 pipelines on the switches as well as on the controller. And I'll show you OpenFlow 1.3 in action in a network. It's also recommended at the moment that you do not increase the number of hardware tables used on Comware switches. So stick with the defaults on ProVision and on Comware. So for the demonstrations, let's start with a simple topology. In this example, I have two ProVision switches. These are 3500 wireless switches connected via port 24, and each switch has one host connected to it. Clicking on OpenFlow Monitor will allow me to view details of the switches. So notice here we have two switches. DPID of the first switch is ending in 80. Second switch ends in C0. The first switch has an IP address ending in 101, second switch 100, and notice please that the first switch has negotiated to use OpenFlow 1.0.0 with the controller, and the second switch has negotiated to use OpenFlow 1.3.0. So in this topology, switch with C0 is using OpenFlow 1.3, switch ending in 80 is using OpenFlow 1.0 with the controller. Now, HP ProVision switches support OpenFlow from version 15.14 of code. So both of these switches are running 15.14 firmware. So why did the one switch negotiate to use OpenFlow 1.0 and the other switch 1.3? They both support OpenFlow 1.3 with this version of firmware. So on this switch 3500 while 1, show run pipe begin open. Notice the switch has been configured to use OpenFlow 1.3 in this instance. This command means that the switch will try and negotiate with the controller to use OpenFlow 1.3. If the controller supports OpenFlow 1.3, the switch will negotiate to use that. However, if the controller only supports OpenFlow 1.0, the switch will use OpenFlow 1.0 with the controller. So this switch, show OpenFlow instance VLAN 10, has DPID ending in C0, and that's the second switch here. This switch, show OpenFlow instance VLAN 10, has a DPID ending in 80, so that's the top switch. Notice we can see in the output that the configured OpenFlow version is 1.0 and the negotiated version is 1.0. So show run pipe begin open. Notice in the output there is no reference to the version of OpenFlow. That's different to what we saw over here, version 1.3. Now by default, HP ProVision switches use OpenFlow 1.0. So even though the firmware of the switch supports OpenFlow 1.3, because it hasn't been explicitly configured under the instance, the switch will use OpenFlow 1.0 as the configured version. That's the default version that's used unless you specify otherwise. On the flow table of the first switch running OpenFlow 1.0.0, notice the table ID is set to NA or not applicable. The controller has no visibility of hardware and software tables on the switch. The controller doesn't know, as an example, whether these flow entries are in hardware or in software. Looking at the second switch, this one's negotiated to use OpenFlow 1.3.0 with the controller. Clicking on flows, notice we see table IDs. Now this version of the controller is 2.3. This version was released in July 2014. In previous releases of the HP controller, such as 2.2 and 2.0, you would have actually seen table 0 in the output here. That's hidden in this version of the controller. You cannot program flows into table 0 on HP ProVision switches. So in this release of the controller, we only see tables 100 and 200, even though table 0 is being used by the ProVision switch. I could view that by telnetting to the switch, so show OpenFlow instance of VLAN 10. Notice the DPID is the same as the switch we're viewing on the controller. Show OpenFlow instance VLAN 10 flow table. Notice the table IDs 0, 100, 200. Table ID 0 has a go-to statement stating that traffic goes to table 100. The policy table 100 has a flow count and a miscount, and so does table 200, software-based table. So on this ProVision switch, which is a 3500 while switch, notice table 100 has some matching packets for traffic arriving on port 1, and the statement is to send the traffic to 200. In other words, send it to the software-based table. The same is true for traffic arriving on port 24. It's sent to table 200 for further processing. I'll extend this a bit more so we can see the full MAC addresses. Notice here we have traffic from MAC address 20 arriving in on port 24, going to MAC address 40, and its output to port 1. Looking at the topology diagram, I'll change the node to MAC address notice traffic coming in on port 24 on C0 going to MAC address 40 is going to be output out of port 1, which is what we're seeing in this flow entry. These entries in table 200 are in software. Table 200 is a software table once again. These flow entries here are hardware-based flow entries because table 100 is a hardware-based table. I can view the OpenFlow pipeline on the switch. So in this case, I've telnated to the switch. So show OpenFlow instance VLAN 10. Notice DPID is C0. Show OpenFlow instance VLAN 10 flows. Flow entry 1, this top entry, matching traffic coming in on port 1, but not matching any other types of traffic. Priority is 29999. Flow table ID is 100, this hardware table. Instruction is send traffic to 200. Notice go to statement 200. Traffic is forwarded to the software table. Scrolling down, flow entry 2, incoming port 24. Instruction go to 200, software-based table. Let's have a look at flow entry 1, 2, 3, 4, 5. This is a low priority entry flow. Notice the priority is set to 0, and the apply action is to send the traffic to the controller. Notice the match is blank. This is called a table miss. If there's no match entry, that means the traffic is going to be sent to the controller. So show OpenFlow instance VLAN 10. Let's begin at flow 5. Incoming port is any. Any traffic is matched, so nothing is being specified. Notice the match on the controller is showing blank. This is a software flow entry. It's put into the software table, and the instruction is apply action controller port. In other words, send the traffic to the controller if it doesn't match any entry in the software table. For the hardware table, we also have an entry. This entry is also blank, so this is the table miss entry for the hardware table 100. When traffic arrives, it's going to start at table 100 in this case. If it doesn't match these two entries, it's going to be classified as a table miss. In other words, it didn't match anything in the table. And the table miss action is to send the traffic to table 200, the software-based table. This then matches on various values, but if the traffic doesn't match anything, it's sent to the controller. So in other words, the controller has written flow entries to the switch saying, if you don't have any flow entry matching the traffic, send it to me. In other words, send it to the controller. Now, as an application developer, you could program flow entries into the hardware-based table because the table is exposed. So when you use the REST API as an example, you could say that a specific flow entry needs to go into this hardware-based table rather than the software-based table. Now, there are quite a number of restrictions on ProVision switches with regards to which flow entries can be programmed in hardware and which flow entries need to be programmed in software. That's often dependent on the device as well as the ASICs in that device. This switch that we're viewing here as an example is a 3500YL switch. This switch uses what's called a version 1 ASICs. It's a very old switch. Version 1 ASICs don't have the same capability as version 2 ASICs. A 3800, on the other hand, uses version 2 ASICs and therefore has more capability for matching and applying actions and hardware when compared to a 3500YL. So now I'm going to show you the hardware table on a 3800, which is a version 2 ASIC ProVision switch, and then I'll show you the hardware table of a Comware-based switch. In this topology, I have two 3800 ProVision switches and two 5900 Comware switches. So let's start with a switch on the bottom left. DPID ends in 1800. Notice in this case we see table 0. That's because this controller is a version 2.2 HP VAN SDN controller. Notice as an example we see table 0 and table 100. What I want to point out in this example is notice flow entries have been written to the hardware table, table 100. Traffic with this source MAC address, zeros ending in 6, going to this destination MAC address, zeros ending in 5, received on port 4 is going to be output out of port 2. So looking at the topology, I'll change the node to MAC address. Notice traffic coming from MAC address 6 to MAC address 5, received on port 4, is going to be output out of port 2. I could specify 6 as the source and 5 as the destination in our topology by pressing S and D. And notice the flow is in on port 4, out on port 2. And that's what we're seeing in this flow entry. The important piece here is that this flow entry has been written to hardware. I, once again, as an application developer, could write an application that adds a flow entry to the flow table and specifies that the flow entry needs to be written to a hardware table, in this case, table 100. As long as the switch supports those matches and actions that I've specified in my flow entry, the switch will allow that flow entry to be written to hardware. However, if the switch doesn't support it, the flow entry will be rejected. So as an example, back on my 3500 YL, older switch doesn't have the same capability as the 3800. So notice these kind of flow entries matching MAC addresses have been put into the software table, not into the hardware table, because the switch doesn't support matching these type of values and outputting to specific ports in hardware. That is an ASIC restriction on the switch. Whereas on a 3800, these kind of entries have been written to the hardware table. Now on a Comware-based switch, so let's look at this switch, DPID ending in 3B. Notice there's only table 0. I'll show you the summary just to show you that it's a Comware-based switch. Notice hardware 5900 AF, Comware-based switch running version 7.1 of Comware operating system. Once again, going to flows, notice the hardware table ID is 0. Comware-based switches, once again, by default, have a single table, and it's a hardware-based table. Everything is done in hardware. There are no software tables on Comware devices. Everything is done in hardware on this switch. So in summary, a switch that's negotiated to use OpenFlow 1.0 with the controller does not expose ASICs to the controller. The controller sees the switch as a single table. Hence, the table ID specified here is set to NA because looking at the summary, notice that this switch is negotiated to use OpenFlow 1.0.0 with the controller. You couldn't write an application that specifies that a flow entry be put into hardware on this switch because OpenFlow 1.0, by definition, only has a single table. The switch could decide to put flows into hardware or into software, but you couldn't control that. On a switch that's negotiated to use OpenFlow 1.3.0, notice the hardware pipeline is exposed. On this switch, which is a 3500 YL, notice table 100 and 200 are shown. On this switch, which is a 3800 switch that's negotiated to use OpenFlow 1.3.0 with the controller, notice we can see table 100 as well as statements to go to the software table. Here's an example specifying that traffic go to table 200, software-based table. On Comware-based switches, by default, there's only a single hardware table, table 0. Now, the tables available in the pipeline are vendor-dependent, hardware or ASIC-dependent, and in some cases, command-dependent. So on this switch, as an example, By default, we see table 0, 100, and entries for table 200. I've telnetted to the switch, so show OpenFlow instance VLAN 10. Notice DPID is the same as what we're seeing on the controller. Scrolling up, we can see that the configured OpenFlow version is 1.3, negotiated version is 1.3. Show OpenFlow instance VLAN 10 flow table. Similar to the 3500YL, we see three tables, 0, 100, and 200. Now, I'll disable OpenFlow, show you the config, so in this case we have a single instance VLAN 10, currently using OpenFlow version 1.3. I'll specify IP control table mode and then enable OpenFlow again. And now if we look at the flow tables, notice more tables are available in the pipeline. Now, because of the length of this video, I will explain this pipeline in more detail and what's supported in hardware and software in a separate video. For now, what I'd like to show you is that when I refresh the page on the controller, notice suddenly the tables exposed to the controller have changed. We have table 0, table 50, table 100, and notice there are references here to table 102 as well as table 200. Scrolling down, notice table 100, table 102, and references to the software table 200. So by changing a command on the switch, I'm able to change the OpenFlow pipeline. I'll try and disable it, but notice on the provision switch we need to disable OpenFlow first, and now I can remove IP control table mode. Looking at the flow tables again, notice we're told that the switch hasn't negotiated to use OpenFlow 1.3 with the controller. So I need to enable OpenFlow. The switch needs to negotiate with the controller to use OpenFlow 1.3. And now notice we are back to having our three tables, 0, 100, and 200. Refresh the page on the controller. Notice table 0, 100, and references to table 200. So we've changed the pipeline by removing IP control table mode. That concludes this video discussing OpenFlow 1.0 and OpenFlow 1.3 pipelines. In summary, OpenFlow 1.0 has a single table. OpenFlow 1.3 supports multiple tables. That functionality started with OpenFlow 1.1. Please go to pakiti.com for more videos discussing OpenFlow and SDN. I'm David Bombal, and I want to wish you all the very best.